just for the sake of simplicity. So each of these 4 red lines is an individual physical qubit. What I'm then going to do is I'm going to find 3 particular couplers on this chip that are denoted by black dots, and I'm going to set those to a strong ferromagnetic coupling. So in my units of dimensionless units of J, I'm going to call that -2. And the whole idea here is that if I've set things up right, I'm effectively going to lock the 4 degrees of freedom of these qubits together. So it gives me a single degree of freedom. It behaves like a single effective qubit. I'm going to replicate that structure 7 more times across this block. So each of these unique colors here corresponds to an individual effective qubit, or will end up being one of my spins on the lattice. Well, of course, at this point, they're non-interacting. So I'm then going to go in and I'm going to declare another subset of couplers to be my lattice couplings. So what I've given by the white points here. And I'm going to set these things, a little hard to see on this diagram, lighting right now, Gij, that's going to be plus or minus 0.3. And the whole point is I want these lattice couplings to be much weaker than these guys. That way I can assure that the qubits, physical qubits, are reasonably well locked together. And there's no way, for instance, if I look at the red guy, say if I apply a signal, strong bias signal at this end, and it doesn't somehow torque this end, and it causes those logical qubits to disagree and break in the middle. So, okay. So let's say these vertical guys, I'm going to call that the A-axis of my crystal. All these ones along the horizontal, I'm going to call that the B-axis of my crystal, so I'm at a 2D layout at that point. How do I get the 3rd dimension? Right along here, along the diagonal. So every time I have a pair of couplers, or a pair of colors intersect, what I'm going to do is I'm going to take a pair of couplers on the processor. I'm going to correlate them. I'm going to say these two have to move in unison. I'm going to set them to the J of plus or minus 0.15, so that way they either sum to plus 0.3 or minus 0.3, depending upon particular instance that I'm embedding here. So voila, you can see now I get a 3rd dimension living along the diagonal of this 2 by 2 unit cell. And of course, if you tile it all out in the 16 by 16, this is what it looks like. So if you just look sort of squintily at the picture, you can certainly see the A-axis orientation, B-axis orientation just goes along with the layout of the processor. Then each of these 2 by 2 blocks, you can see a 3rd axis running off the diagonal. So this is my 3D structure. So it ends up with this 16 by 16 unit cell processor. I can embed up to an 8 by 8 by 8 cubic lattice, which is getting, on the edge of respectable. From what I've gathered from the experts who do these sort of transverse lighting models, they're telling me that something like 14 by 14 by 14 is getting pretty tough on a decent computer these days. Okay, so now on to the good stuff here. What are we going to do with it? So I'm showing you how we can stick that 3D structure into the processor. Now how do we slice and dice that space and actually get some useful information out of it? So I think it's best just to boil it down to a few specific objectives. So we're going to measure a few particular things and try to fit the pieces together. So the first thing we should be able to do is actually measure that critical doping that I showed you earlier. So that PC equals 0.222. That's just a classical problem. All I need to do is run my quantum annealing algorithm right to the end. I'm going to study an ensemble of instances as a function of doping P, and I'm going to look for some sort of critical behavior and pick out where that occurs. Next thing I'm going to do is I need to implement a measurement for picking out phase transitions. So if you're a bred-in-the-bone experimental condensed matter physicist and you've been handed a sample of a magnetic material, you're said, there's a magnetic phase transition, find it for me. What's the first thing you're going to do? You're going to go to your AC susceptometer and you're going to measure linear susceptibility. So we're going to indeed implement the linear susceptibility measurement. The other thing we're going to do is we get to actually measure order parameters in a very nice way. Because unlike a macroscopic system in the laboratory, so if I had a single crystal of something, pretty much I can measure things like an overall magnetization of that sample. But if I want to get fancy and measure something like a staggered magnetization or an AFM magnetization, I can't do that with my with my susceptometer in the laboratory. There won't be any signal to measure at all. However, recall that this is a processor where I can go in and read every single individual physical qubit. So I can actually read the state of every one of those logical qubits to build the spins in this lattice. So then I can do all sorts of fancy tricks, and it really neatly ties into some of the computational methods people use to study these systems. So in particular, we're going to look at magnetization. We're going to look at an order parameter called the spin-spin overlap. Impossible to produce in the lab, but guys do numerics do it all the time. And we're going to be able to clearly distinguish between the paramagnet, antiferromagnet, and the spin glass. And finally, put all pieces together is we actually want to map out that doping transverse field phase diagram, presumably at some low temperature. I'm not specifying the temperature here. I think that's going to take a lot more work out of our experiments to decide where the phase transition happens, actually go in and calculate what I think the effective temperature is going to be. As long as it's low, I'm going to be happy. So, everyone following so far? Everyone see the 3D lattice measurements going into it? Okay, so I'm going to start out with the very simplest measurement you can do, and that's just measuring the magnetization of this system. Perfect. This is the simplest thing you'd want to do with whatever magnet you have in the lab. The way we're going to do this is we're going to run a pause, or an anneal, pause, and then quench annealing profile. So as before, when I was discussing, for instance, factoring yesterday, what we did is we ran this annealing parameter S from 0 to 1, and we just looked at the output at the end of S equals 1. We're just presumably gently guiding the thing through some phase transition, if we're lucky. Not so gently if we're not so lucky. What I'm going to do here is I'm going to slowly ramp myself from S equals 0 up to some intermediate S where I want to study my system. I'm going to hold it, and I'm going to hold it for a long time, milliseconds. All I want to do is just let this thing relax, equilibrate to wherever it wants to be at that particular intermediate value of the transverse field. And then I'm going to try my best I can to quench this thing. The idea there is if the dynamics of the system are relatively slow, and I rapidly pull up that annealing parameter, then I'm going to take a snapshot of the state of that system. This is definitely not a projective readout. If I start very early in the anneal, so my target value of S is very close to 0, what's going to happen here is typically I'm going to be deep into a paramagnetic phase. And there, as I pull up that S, the system is going to still respond to me very, very quickly, and it'll probably adiabatically follow me for a while. And then you can think about that Kibble-Zurich mechanism as we go sort of blasting right through that phase transition. And then I end up with domains locked all over the place. However, once I sort of asymptotically approach a phase transition, though, if you recall from my first lecture, that relaxation time scale is diverging. So at that point, I start to begin to faithfully snapshot what's going on in the magnetization. I'm also going to keep my longitudinal fields at 0 for this particular measurement. So I'm going to try to maintain that Z2 symmetry for this particular measurement. Okay. So what I'm going to do is, like I said, slowly anneal, quench, and I'm going to repeat that 1,000 times for each particular instance. And I'm going to just do this as a function of S. We'll see what happens. So here's an example of some of those magnetization data. So this is just one particular instance at P equals 0.1. So what I have here is on the horizontal axis is the annealing parameter S, that target value where I pause my anneal. Vertical axis is the AFM magnetization. Recall that my P equals 0 undoped state is an AFM magnetization, so that's spin up, spin down, spin up, spin down, and then the other reverse spin down, spin up, blah, blah, blah. So I'm going to track that as my order parameter. Plus and minus 1 are perfect AFM ordering, and obviously 0 means completely jumped up, no correlations between those spins. As I start early in anneal and S, you can see there's just sort of this rough cloud of magnetization here. Oh, pardon me, I should back up. What's happened here is that each column of points here, I've stopped at a particular target value S, done 1,000 measurements, and then I've histogrammed the magnetization that I've seen thereafter. So if I just take a vertical slice right here, what I actually get is a big broad Gaussian right around 0 magnetization. That's what you see for the paramagnetic phase. It just looks like a Gaussian distribution of magnetization. Now, as I run this annealing, my target value later and later, that's where the fun happens. You can see roughly around here, getting close to S equals 0.22, all of a sudden the magnetization quickly bifurcates, and then you see these two peaks come up. So of course what's happened here now is it looks like we see an onset of the AFM magnetization. This is beginning to smell like a phase transition now. Now notice that that's about plus or minus 0.95. It's not perfect AFM ordering, and that's because of the doping here. There's 10% doping of those bonds. It means I don't have that perfect ordering all over this place.
That's a quick question.
Yes.
So you said that these are counts of different runs that you did. So this is measuring some order parameter where you measured the alternate direction of magnetization on alternate sites. So I noticed that the counts are much higher on for one of the possible orders.
Yeah. That's right. Yeah, you do indeed see a bias in here. So that's an interesting one. So it ends up, we are actually seeing hints, what looks like hysteresis that's induced by the environment around the qubits. So digging into the details of the devices, it ends up, we actually see magnetic defects living close to our wiring. And what's happening is when we run this quantum annealing algorithm through the completion to do our readout, there's a fairly large persistent current running around these qubits. It's about 2 microamps. That current is enough that actually polarizes the spins in the environment around the body of the qubit. It actually leaves an imprint of where this guy had been last.
I see. So,
And so next time we anneal it, it sort of gets dragged back towards that state, just a bit.
so do you think this would be a problem for not just this calculation, but like your quantum annealing simulations in general,
Yeah.
this sort of thing?
Absolutely. So what we've learned is that there is a relaxation timescale associated with that, and we're also learning how to kill it in the fab process too. So
Can I ask one question about
Yeah.
that? So from the width of this peak for very small s, can you extract the temperature of the state,
no,
or-
it's primarily, it seems to be related to this quench rate. So unfortunately, it's because I have these relatively low bandwidth bias lines in my system. I only get to snapshot the thing really faithfully when I get very close to the phase transition. So what's happening is this thing could actually be very tight distribution back here. And then as I run into the phase transition, it's starting to fan out, and then I got a snapshot of that fanning out somewhere. Okay. All right, so that was just a brief segue just to show you what some of those raw data look like when we run that magnetization measurement. Let's get back on track here. I said the first thing I wanted to do was find that critical value of doping. So as I said, that was a classical problem, so we solved that. We studied that classical problem by running quantum annealing through to its completion. So the way we're going to do that here is I'm going to produce an ensemble of instances at multiple values of p. And I'm going to measure the mean magnitude of the magnetization at s equals 1 for that ensemble and look for that mean, and of course put my error bars on it thereafter. So what you see here are 3 sets of data. 3 different colors are for 3 different system sizes. So I made a 4x4x4 cubed, a 6x6x6 cube, and an 8x8x8 cube. The reason why I'm doing this is because the experts who work in this field will tell you you need to be very aware of finite size effects. So this is one way to help me tease those out. So what I've done is for each of these points here, it represents up to 600 instances at a particular value of p. So I choose a value of p, and then what I'll do is I'll just randomly choose a set of bonds to put to the ferromagnetics, put the j equals -1, and I'll produce like 600 of those guys, run them all, calculate mean magnetization off of those guys. The other trick I do here, of course, is some data post-processing, is that, as I said, this is a classical Hamiltonian at the end of the day. I run my annealing algorithm, I get my solutions out. Well, guess what? I can always take my solutions and put them back into my Hamiltonian that I know I programmed the hardware. I can check their energy. So the neat thing I can do there is that if I've got 1,000 solutions coming back from the hardware, I can tell which ones are the lowest energy. That's dead simple. Are they the ground state necessarily? No, I can't guarantee that. But however, they're going to be pretty close to what's represented with ground state energy. But if anything, there'll be a few bit flips off. It's good enough. So once you have a system that's 8x8x8, that's 512 sites. If I have one spin that's not in agreement with the ground state, well, that's getting down to my measurement point. So I'm not going to worry about that in terms of the magnetization. So I use that as a filter. I just look at the energies for each particular instance. I take my lowest energy solutions.
So when you say you run an experiment 600 times, do you also change your randomly selected connections for every run, or is it the same set of connections just run 600 times?
Yep. So I'll have 600 unique combinations of random dopings, or pardon me, random bond configurations. I'll run each one of those 1,000 times. So lots of statistics.
So each point on there is 600,000 experiments.
Pardon?
So each point on here is 600,000 experiments, essentially, or trials, right?
Yes, correct. Yes. Okay. So the reason, back to where I was, I said we've done this filtering by energy. The idea there was I just wanted to know what does the magnetization for the lowest energy solutions look like, and then I take the average over that for my ensemble for a particular value of p. So that's what you see on this plot up here. So starting with the smallest system, you can see it's a monotonic function that's dropping down as p increases. Of course, course, just increased doping. We're seeing that order parameter break down. As you go into larger and larger systems, you can see this thing is starting to pick up, and then it drops down here. But regardless, you still see these big long skirts that are coming off here. And of course, the experts will tell you, well, that's finite size effects in the end. Yes.
Sorry, what do you mean by filtering by energy,
All right.
precisely?
Yeah, so for any particular instance, I run it 1,000 times on the hardware. So I get 1,000 solutions back. I know the Hamiltonian that I programmed into it. Just calculate the energies. It's like an NP hard problem. I'll do the P part, which is just verifying it. And then I just take whatever's giving me my lowest energy at that point. Okay, so as you do something like this on a finite size system, of course, you can see that the magnetization never quite goes to 0, and that's because the correlation length eventually has to hit the boundaries. It has to hit the size of your system. So as I pass through these phase transitions in a finite size system, well, eventually I always get a domain that's stuck to the size of my system. I never see the true phase transition by just looking at the order parameter on finite size systems. So I went to the experts and said, well, how do you deal with this in your numerics? And they said, well, you have to look at higher order moments for your magnetization distributions. I said, go look at this quantity we call the Binder cumulant. And this is what I've written and called G up here up in the top. So I'm looking at something that's a combination of the fourth order moment divided by the second order moment. It's really about trying to assess when is this distribution, the order parameter, making a sudden distribution that's clearly non-zero to something jumping with mean that's getting close to 0. So if I crunch those data through for those 3 system sizes, those are the points that you see here. And it ends up, this Binder cumulant becomes a scale invariant quantity when you're sitting right at a phase transition. What that says is you're looking for a crossing in all these data. So I've done the best I could, put error bars on these things, I fit just polynomials to them, and then I can give a bounded estimate of where I think that crossing is, and the value what I get is 0.22 plus or minus 0.01. So recall the literature value that I pulled out was around 0.222. Run on numerics, and this particular gentleman ran up to, I believe it was like 16 cube size lattices to pull this out. So I think reasonable agreement. It says that at least we should have confidence we're putting the correct final target Hamiltonians into the hardware, and we are seeing low energy states that are representative of what we should see. So of course, as I said, this thing should obey some finite scaling laws. So this G should be some function. I don't know what it is. It scales as L, the system size, to an exponent, and then relative to a critical doping. So you work out what that scaling looks like, and this is sort of what the best fit looks like. And then you pull out a 1 over nu, this exponent comes out 0.85. Literature result was 0.9. I should put an error bar on that thing. Shame on me for not doing that. I will do that. But more or less fitting together. It looks like we have actually done a finite size effect study on a condensed matter simulator. So I've always quipped that, of course, this is the first time as a condensed matter physicist I've ever had a finite size effect problem in my sample. Usually we're thinking, 10 to the 20 something atoms in our system. We're not worried about this, but times have changed. Okay, so that's my critical doping. Well, let's go on to looking for that transverse field effect. We want to find phase transitions as a function of the transverse field. So the first measurement, the measurement I'm going to implement to do that is a linear susceptibility measurement. And it's going to be a variant on that magnetization measurement that I'd shown you earlier. So again, I'm going to use this annealing profile where I start out gently anneal, pause for a good long while, let things equilibrate, and then quench as best I can given my bias line constraints. But now, when I do this measurement, I'm going to first start out at 0 longitudinal field on these spins. And then as I go into the pause here, I'm going to first toggle it up a little bit. And I'm going to repeat the experiment, toggle it down a little bit, and I'm just going to gather lots of statistics flopping back and forth between these two. And the whole idea is that if I've made that variation in the longitudinal field small, I'm going to get something that approximates the linear susceptibility. So I'm going to do one more trick though, is recall that the system as p equals 0 is an antiferromagnet. So if I went and applied a uniform longitudinal field to the system, it would do nothing to it. It would just take an antiferromagnetic ground state, and it would look at the longitudinal field and say, so what? Push it the other way, nothing would happen. So the trick I'm going to do here is something you can't do in a laboratory with a macroscopic sample, is I'm going to take that longitudinal field and I'm going to apply it up on one spin, down on the next spin, up on the next spin, down. I'm going to apply the staggered magnetization because I can actually do this on the D-Wave processor. So now I can actually probe an antiferromagnetic susceptibility. This is really cute because when people in the condensed matter world want to study an antiferromagnet, the first thing they have to run through is neutron scattering. The reason there is they're actually trying to do a spin-spin scattering experiment to actually pick up on the antiferromagnetic order parameter. Meanwhile, if their brethren, studying a ferromagnetic system, what do? They go to their little wee AC susceptometer sitting in the corner of the lab and go measure their stuff. So it's quite a dramatic difference between the scale of the experiments to get an antiferromagnet. Okay, so here are some maps of that AFM susceptibility versus S. The way I've produced these, let's see, just check. Yeah, for these particular data, they're just sort of run fast and dirty. All I did was I took 3 randomly instances from that ensemble of instances that I discussed earlier in slides, measure their susceptibility and average the results. Just have to average out some noise. I should admittedly do this measurement over many, many more instances just to really clean it up. So what one sees is I'm showing you 5 particular values of the doping. These are all below the critical doping. So this is all paramagnet to antiferromagnet. So it should all be sort of the same phase transition. What one sees is that you see what looks almost like a plateau back here, and then eventually sharpening up and crashing down. So, and of course, that's the sort of thing that makes the condensed matter experimentalists go, oh, thank God. I actually see a divergence in the susceptibility happening. That is one of those hallmarks of a second order phase transition, what you'd expect for this paramagnet to antiferromagnetic system. So it really does look like we're actually hitting some sort of critical point with a phase transition. Now, as for what's happening back here at low S, this goes back to this issue of quench. So as I told you, I had a finite bandwidth on these bias lines, and I can only pull up my S parameters so fast. So if I start very early in the anneal, I'm grabbing that system, it's adiabatically following, then it's hitting that impulse region as I described earlier, and we're going through phase transition sort of a la Kibble-Zurich mechanism. So you can see what's happening is I try to sample way back here, it's too early, and I get close, and then finally I'm starting to outpace the dynamics of my system as I approach the phase transition. So I finally, at least with this measurement, I'm able to see the peak, but I'm not quite able to resolve what's going on back here. I just tried some experiments last week before I came here with a new system. We've actually increased the bandwidth on these bias lines by a factor of 10, and I can see these tails dropping down ever so nicely. So it looks like, again, we got the right physics going on there. So as we increase the bandwidth and we tweak our experiments, I'll be able to see more and more of that stuff happening. Okay, so as a function of doping, you can see that the peak starts to move later and later in the anneal. So it's going to larger S, which means smaller transverse field. You also see the height of the peak getting crunched down. And eventually, as we're getting close to that critical doping, it looks like the peak really gets squashed out. And you can see this guy, it almost looks like there's two peaks in here. And it's because these instances, as you approach the critical doping, they start to get pretty schizophrenic. It's pretty hard to, really, it's having trouble trying to decide, am I an antiferromagnet or am I a spin glass? So this is a case where you really need more statistics to really pin down what's going on there. So that ends up being a very awkward region, both in these experiments, and when I talk to the guys who do the numerics on these systems, they say, yeah, that's the trouble point for all of us too. So not a giant surprise. Okay. As we go to the other side of that critical doping, now we see a slightly different phenomenology happening. It looks like the peak pretty much stalls as a function of S. It looks like it's more or less in the same spot. And we just see the amplitude getting squashed down as we increase doping here. Really, in this case, it looks like there's no longer what you would say it looks anything like a divergence in the susceptibility. So no longer really a clear signature of phase transition. And of course, when I've talked to the experts about this, they say, well, if you're looking at paramagnet spin glass, well, no wonder. The divergence is actually gone in linear susceptibility. You need to implement a different measurement, and that's called spin glass susceptibility. Unfortunately, I don't have those slides ready yet. That is a much more difficult measurement to implement. We're working on that right now. But nonetheless, this peak does survive, and it still gives you a hint where something's going on. So next slide, all I'm going to do is I'm just going to scale all these data by the maximum value of the susceptibility here, and just show you that the peaks are indeed surviving all the way up to that point. So all the way from peak was 0.25, 0.5, obviously getting much noisier. And the whole AFM order parameter is completely broken down at that point. There isn't much left to really kick around. But you still see there is something happening there, and then we're dropping off. Okay. All right, so we've looked at the magnetization. We used that as a probe to pick out where do we see the critical doping, where do we see AFM ordering breakdown. We've looked at linear susceptibility, at least on the paramagnet AFM side, we can see a clear phase transition. That's easy to pick out. On the paramagnet spin glass side, maybe it's not the best signature, and maybe we need to work on that a little further. However, there's something that's still missing here in the end, is I can't really tell the difference from any of those measurements between a spin glass and a paramagnet. So as I look at those lumps that I showed you for the paramagnet to spin glass phase transition, how do I know something's really happened between those two cases? Can I actually pick out any difference? The answer is yes. I just need to look at a different order parameter. So it's no longer just that simple AFM magnetization. So the order parameter that's been proposed is something that's called spin overlap. And it's this quantity I've written down here is Q. And the idea here is that if I take two copies of my system, or I perform two independent runs of it, and I push it through, I run through, and I just compare my two solutions that I get at the end of the day, I'm going to ask, what's the inner product of those two? So if I have an ordered system, for instance, what I expect is that those two answers are going to line up very well with each other. And so my Q will be 1. Or it could be -1, for instance, in the antiferromagnetic case, because maybe I'll run, I'll get one configuration. Next time I run, I'll get the other configuration for the ground state. Take the inner product, I get -1. However, you get a much more confused looking and more rich distribution of Q when you look at the spin glass phase. So the whole game we're going to play here is we run our system 1,000 times in any particular instance, a particular target value of S. We're going to calculate a whole bunch of values of Q. So we're going to get about 500,000 values of Q, and then we're going to calculate a distribution for those things. We're going to histogram them and just turn into a probability of Q versus Q. And we're going to look at that. So for an infinitely large system, it ends up this measurement of probability of Q gives you a very clear fingerprint between these different phases. If you're in a paramagnet, what you expect is a delta function sitting right at Q equals 0. So you expect thoroughly uncorrelated answers to come out of the hardware every time you run it. If you have something that's clearly an ordered phase, like an antiferromagnet or ferromagnet, as I've said, where you have two spin flip symmetric ground states, there's only two possible values of Q at that point, ±1. And as you go into the spin glass phase, well, that's where all the wildness happens, is rather than getting those two spikes that you get on the ordered type phases, here you see peaks that aren't exactly at 1, and they come in correlated pairs all over the place. Yes?
So if you have ferromagnetic or antiferromagnetic domains, can't you still get values of Q between -1?
Yes, you will. Yeah,
Okay.
absolutely. Yeah, so if you have a fractured state, so if you, for instance, Kibble-Zerk mechanism, you just took a paramagnet, antiferromagnetic transition, you drove it really, really fast and broke it all up. Yeah, that distribution of Q is going to look a lot more like that.
So do you just, for this, do you just do this carefully and slowly enough to avoid
You
that?
try your best to be as careful and slow as you can. Yeah. Okay, so we'll start out first is we'll just look at paramagnet to antiferromagnet. Here's experimental maps of P of Q versus Q. This is just, again, 10% doping as a representative example here. What I've done is I've calculated this distribution for 4 different values of S. I've chosen S equals 0.1, so that's deep in the paramagnetic phase. I've chosen S equals 0.3, that should be deep in that ordered phase. And then I've just chosen 2 representative values of S, roughly straddling where the phase transition occurs. I just wanted to see what was going on just for the hell of it. So once it starts out, S equals 0.1, you see that big, broad Gaussian sort of distribution here. Again, it should be fairly sharp, but because of that finite speed at which I can pull up my barriers, or this annealing parameter S, sort of gets broadened out before it gets frozen. However, upon approaching the phase transition, you can just barely see it here. There's sort of a residual of this peak that's left here, and then things start to get pushed out very fast into these sort of pinpricks at ±1. So you can see, as you expected, is that this P of Q is behaving itself quite well on the paramagnet to antiferromagnetic side. Once you go to the spin glass phase, then you get these more exotic looking maps. So here again, I've taken 4 particular values of this annealing parameter S, again, just above and below that phase transition, and then 2 relatively close. So in the paramagnetic phase, here you see a much sharper Gaussian. The reason there is because the overall dynamics of the spin glass phase transition are that much slower compared to the antiferromagnetic phase transition. I'm actually able to lock the spin distribution much earlier, much more faithfully. Now, once I run into that paramagnetic spin glass phase transition, you can see that it really looks like the distribution gets squashed down, almost like a block, and then spikes all over the place. And as I run later in the anneal, you can see that these spikes that are closer, they're getting up close to plus or minus 1, and they start, more weight starts going out there. You can also see, though, there is an asymmetry to this. So recall my little cartoons from the preceding slide, where I says those peaks should be coming in symmetric pairs if all is behaving itself well. However, what you can see is it almost looks like the distributions are a little bit biased over this way, towards the positive side. This goes back to this problem that this gentleman picked at earlier when we looked at the magnetization as a function of S and looked at those distributions. You can see that we're a little biased to one side. Same problem here is that the environment around these flux qubits is actually carrying a memory of where it had been before and is trying to sort of draw the system back into those same states over and over again. So what that means is that you end up biasing yourselves toward positive values of Q a little bit. Nonetheless, the structure's there. One has to be incredibly patient to see some of these things, though. The anneal times that I was running for a lot of the antiferromagnet stuff was, millisecond was plenty. It was complete overkill. I've been running these experiments at 10 microseconds, and they looked about the same. No big issue. However, once you go in the spin glass phase, you can see I'm starting to approach annealing times that are looking like orders of a second. And that's not too surprising once you get into a spin glass phase. The dynamics of these things are incredibly slow. Okay, so tidying up here, I said the last thing I wanted to do was put all the pieces together to look at this doping and transverse field phase diagram. So first, I'm going to just show you raw data. So what we do measure is critical values of S from the susceptibility measurements as a function of doping P. So these black dots here with the arrow bars, those are from my estimates of where those peaks in the linear susceptibility. It's the best that I've got, say where the phase transition is. Should be pretty good in that paramagnet, antiferromagnet. Spin glass phase, we'll have to be careful there. We also know our critical value doping from the experiment. So I've got my critical value of 0.22. I'm just denoted by this vertical dashed line here. I can't say for certain that this boundary in the phase diagram is vertical because I haven't actually done an experiment where I go across this direction. Pretty neat trying to think about what does a susceptibility measurement look like that, where I'm actually varying doping in situ during the experiment. Something you certainly can't do if you've got a crystal. Once you've got your doping, you've got it. However, with the processor, I'm starting to wonder, can we actually come up with some sort of nifty measurement where I start toggling my couplings on the fly here. See if we can actually go that direction. So, as I said, you can see a big paramagnetic phase, the antiferromagnetic phase, and the spin glass phase, which we've identified just by looking at the right order parameter, whether it be magnetization or the spin-spin overlap. Okay, so now the interesting part is, can we actually convert that S into a transverse field measurement? And the answer is yes, there is one way we can posit to do it. As the D-Wave processors, part of the calibration of getting these things set up is we end up knowing essentially all the device parameters, which means that we can then calculate quantities. For instance, like those 4 long logical qubits. Recall how I built up this lattice. I took 4 physical qubits, locked them together with strong ferromagnetic coupling, tried to make them into a single object. Well, I can take my device parameters, and I can actually calculate what the energy gap between ground and first excited state looks like for that 4 long object. And if I say that's my transverse field splitting, if I just call that my gamma, then this is what I get from my translation. So here's gamma over J. J also comes out of the processor parameters. That's related to qubit persistent current, and then all the mutual inductances for all the couplers that we calibrated on chip. So now I have this dimensionless quantity gamma over J on this axis and P on this axis. So I've done my translation. This is what the map looks like. So again, the black points are those measurements of linear susceptibility, trying to pick off the peak. I've got my critical doping, again, the vertical dashed line, those 2 to the side representing my error bars on that. And then the 3 phases just we've identified. I've also thrown on the literature values of all these points that I showed you earlier. So particularly for the clean system, or the P equals 0 system, gamma over J is 5.2, not looking so bad. We of course have our critical doping. We got 0.22 from our experiment, 0.223 over there. So again, not bad. Over here on the spin glass phase, our latest estimate from theory Yeah, that's outside the error bar at this point, so we're starting to wonder what's up there. And I think we've sort of hit on the problem, as I alluded to when I showed you that spin-spin overlap picture, is that the relaxation timescales get incredibly long for these systems as you go deeper and deeper into the spin glass phase. So in particular, when I ran those susceptibility measurements, as I said, I was waiting for about a millisecond and then turning on my longitudinal field back and forth a little bit. I need to try this where I actually go up by a few orders of magnitude in timescales and see what happens. I would not be wildly surprised if these things start moving down. But of course, the other thing I need to do is actually implement the spin-spin or the spin-spin susceptibility measurement.
Excuse me, you mentioned early on that the annealing path is actually in the plane, where you're reducing quantum fluctuations, but also you could be reducing partially thermal fluctuations. So in establishing this plot that you're showing, do you make any assumptions on J's variation as
Yes.
the parameter S is?
Yeah, so the J variation I've handled in this translation here. So that is part of the processor calibration. So the gammas and J's that I give you are from device parameters. So, but you have sort of hit on the edge of something, which is that there is finite temperature involved.
Yeah. How do you exclude thermal fluctuations?
Yeah.
Could those account for the
Yeah.
deviation that you have from the
So
calculation?
yeah, we don't think so at this point, and the reason is because we've been trying to, on the backside of all this, of course, we've been running our simulations, trying to get quantum Monte Carlo code up and running to see whether we can actually track what's happening. And what we're seeing from those simulations so far says we should still be looking fairly close to a low temperature regime. So just looking, you can actually pick out where the phase transition occurs, and if you just say, all right, my system thermalizes right there, and you calculate gamma over J, well, then T over J ends up being small at that point as well. Okay, so as I said here, it's encouraging. I think there's certainly lots more to do here. It's nice to be able to see that we're actually able to connect finally. We've built a very large-scale device, and we've finally been able to sort of circle back and connect with more physical or natural type systems. We're actually simulating things that 20 years ago people were doing simulations on this sort of stuff, transfer sensing models, and the connections to real experimental systems were quite difficult. Because typically the sorts of materials that you would get for doing this sort of stuff, well, the doping's all over the place, you have domains, crystal domains all over the place that are fractured. You never quite get this idealized sort of cubic lattice with all the Ising spins and the random variations. So this really gives us a nice tight connection to the literature. So we've spoken to some people who've obviously worked in this field, and they're getting quite excited about all of this. Okay, so just tying up in here. So the message I want to leave with you is that despite the fact that the D-Wave processor is inherently two-dimensional, as I showed you yesterday, you can do 2D embeddings of circuits, for instance, giving you NP-hard problems. You can actually do physical 3D systems on it. And besides just this 3D system, you can actually do other lattices as well. We've got folks that have just started working on Kagome lattice on this system now. There's lots of neat stuff coming out of that. The other message I've been telling people is that really start to sort of turn your head a little bit when you're looking at D-Wave processors. We've had a lot of people focused on just looking at, do I achieve the ground state? How fast do I get there? Yes, a very relevant question. Obviously, people are looking for the computational advantage from the processor. However, me as a physicist, I sort of looked at the thing and said, great, I can build a magnet out of this. So why not bring all those magnetism tools to the table and start playing with this? So, measuring order parameters, measuring susceptibilities, dream up what you will. If you've done it to a magnet in the lab, you can probably find a way that we can actually turn that into code and run it on the D-Wave processor. Results are encouraging, but I've got a lot more to do, a lot more than I can do personally, so I'm trying to get a graduate student to work on this. But, I have to find funding. That's what I'm told every time by my management. So it's like, you want to take an employee's salary and hand it to who? So, but okay. These next steps. So one of the things we can do, of course, is play with energy scales. So this FM coupling used to bond these devices ends up. I've got more available, sort of as an experimental mode on D-Wave processors. I can get that going. Big thing I'm looking at is spectroscopy. If you recall from yesterday's presentation, I showed you a spectroscopy on an 8-qubit ring where we actually looked at the energy space between ground and first excited state. I'd like to be able to do that with my 4-qubit systems. I've tried, but we don't have enough precision for what we need. So I'm working on developing new techniques to improve the precision there. I'd really like that translation from S to gamma over J to be based on something from experiment as opposed to just trusting my device parameters from calibration. Implementing a considerably faster quench. I really want to move earlier and earlier, just to avoid that whole Kibble-Zurich type physics where I'm seeing adiabatic evolution and then hitting the impulse phase. I want to move that impulse phase back as early as possible, see what's going on. In particular, the reason why that matters is because when I first showed these data, and rightfully so, every theorist jumped up and said, wait, can you give me critical exponents? And I mean, that's, of course, what I'd love to do is be able to sit, just below that phase transition and measure something like that susceptibility and pull out a power law from that thing. So this, right now, the limited bandwidth and this whole Kibble-Zurich physics is being an impediment, but the faster I can quench this sort of thing, the more I can see that roll off, and the more I can trust that power, whatever I fit to that power law. Okay. And finally, as I said, I haven't described this measurement, the spin glass susceptibility measurement. So just like linear susceptibility is sort of like a first derivative of that magnetization, that easy sort of order parameter to calculate. You can do it with the spin glass susceptibility and do a first derivative of that thing. It ends up being like a chi cubed with respect to this, the qubit moments or that magnetization. It's a vastly more complicated measurement to implement. Should be doable, but I just need time to do it. And with that, I'm going to finish early because I like finishing early, and so does everyone else. So.
So, if you're interested in actually in trying to observe properties of the phase transition with this, would you say that this system is, in its current state, a good candidate for finite size scaling type methods?
Yeah, we do what we can. I think the issue is the limited size of the finite size. So like I showed you, I've got an 8 cube lattice at this point. So go with 4 cube use. It's fast enough right now for doing. The issue is the quench actually. So as you go to a 4 cube system, the dynamics are so fast that you can just barely capture things like phase transitions. So for instance, you could do studies of susceptibility as a function of system size, and then you try to extrapolate from all those peaks. Do finite size scaling that way. I'd like to see more system sizes before we can really do that. So next generation processor, which we're doing. So,
And what is the practical limit on the system size right now?
so practical limit, imagination, of course. Next, all I can say right now is that we are building a much larger system. We'll be targeting, hopefully, at least doubling each of the linear dimensions in that qubit glass next generation processor. At least more qubits, more couplers, less noise, all the good things that we want in a quantum processor, of course. So. Well, thank you very much for listening to all this too. It's always fun to get out of U8. And hey, every time I come back to an academic institution, I see all you young people. I feel old. Thank you for reminding me.
Yes,